it has to be downloaded in the YouTube.
The last?
Yes, class 3.
The one, the Friday? Yeah,
Yes.
the class 3.
Yeah?
Ah, what happened? It is not there?
It's not there. Do you know what? No?
We did something wrong here, probably.
Oh.
It must be. I hope this works. Right, let's see. Okay, let's see. There is a this is the stop. No, I think this should be on now. Okay, hopefully. So check next time if. Okay. So let's move on with this review. Quantum mechanics. We discussed. We will go back to. Yeah.
Can you turn it on again? Because I think you paused it.
No, here I pressed the red button.
So yeah, okay, so it's
Is it?
I think because you paused it again to check if it was working. I don't know if you press it again.
The red one is flashing.
Okay, so
Is it? This should be okay.
Okay, yes. Fine.
Yeah. So we discussed time evolution, right? And we derived the Schrodinger equation. For the state. This may depend on time. So this is time evolution for the state. Okay. This gives a solution can be written as psi of t, right? Is u of t naught, say psi of t naught, where u is the time evolution operator, which has all the properties that we want. In particular, it is unitary because it must preserve length of the vectors, right? So it must be a unitary operator. U dagger is u to the minus 1. And in the simplest cases where the Hamiltonian is time independent, this is very simple. It's a very simple operator. Is the exponential IH t, say, minus t naught over h bar, right? This is the time evolution operator. In the cases where h is time dependent, there are, I mean, if h a different time commute, then it is still a simple expression in which it involves the integral of h from t naught to t, and the more complicated cases where the Hamiltonian different time do not commute, in which case you have the time ordered. Okay, so that. But we will always discuss examples where this is true. Okay. And so in this case, I mean, you have then the states evolve, and then expectation values depend on time in general, right? Because they are therefore psi of t, a psi of t, right? And this is time dependent, and of course they don't depend on time in case where this observable a is commutes with Hamiltonian, right? Because if a h is equal to 0, then you can pass through a here, this exponential, and then they will cancel. No, this is e to the I plus I h. This is e to the I minus, and then when you go this side, this cancels. You get the same. So then a d dt of a is equal to 0, but in general this is time dependent, and so this is like written more explicitly, time t naught, this is u dagger, right, and then a u and psi of t naught, right? This is what it is. Okay. And yeah. So this is what is called the Schrodinger picture, where we don't evolve the observables, but we evolve the states, right? Here A does not have any time dependence. Of course, everything can have an explicit time dependence, right? Like the Hamiltonian, for example, no? But we are not assuming that. We are assuming there is no explicit time dependence. The time dependence arises only through the Hamiltonian evolution, no? You remember also in classical mechanics, the time evolution of a quantity is the Poisson bracket with Hamiltonian, plus there may be a partial derivative with respect to time, which means that the observable has an explicit time dependence. Okay, this is always possible. Now this, okay, so this is Schrodinger picture. And but this suggests, this expression here suggests an alternative picture in which you do the other way around. You keep the state of the system fixed, not evolving, and you evolve instead the observable. And the key is here, right? You can consider now that A evolves in this way, right? So I define A of H, say, which is U dagger, A, let me call S for Schrodinger, U, right? Okay, and now, okay, if you have U, you can compute this, and you will have some, generically, some time-dependent operator, right? If, again, if in case where A does not commute with the Hamiltonian, right? And, but it's more sort of suggestive to, from this relation, derive a differential equation obeyed by A of H. I mean, we want to evaluate I H bar d A H dt and see what this is, because this will be something which is very similar to what you have in classical mechanics. Remember, in classical mechanics we said d dt is HA, say, okay? This is Poisson bracket, no? This is the plus possibly dA dt, okay? Now, how can we derive a differential equation for the Heisenberg picture operator? Well, just from this, right? Because we act with the time derivative on the various terms here, right? So you have to apply I H bar d dt, and then U dagger A U, right? This is the Schrodinger A, which suppose this does not have any time dependence, so that when you act here you get 0, okay? But then you act here and here, right? So you have I H bar d U dagger dt times A S U plus the other action here, right? U dagger A I H bar d U dt, right? This is what it is, right? But we know what are the equations for U, no? This, what this is, and what this is, right? Because remember that the Schrodinger equation is nothing but what we obtain, the equation that we obtained for the time evolution operator, right? For time evolution operator, we got an equation which was very similar to that, right? When I write it here, I h bar du dt is hu, right? This was the version of Schrodinger equation. And this is the Schrodinger h, right? Okay, so this we can use here, right? On the other hand, we have the action on u dagger, so we have to take the admission conjugate of that. So I h bar du dagger dt is the admission minus, because the I here, right? Minus u dagger h, right? H is admission. Okay, so you have to use these two equations here. You can substitute here this one and here this one. So in one case H is on one side, and in the other case H is on the other side. So what you get, if you work it out, you get an equation which involves the so I h bar d h dt is the commutator of h bar of t. Okay. I'm not sure about the sign. Let's see if this is this or the other way around. No, it's this. And here, this, strictly speaking, you have a H Heisenberg, which means that you should conjugate H also with this operator. But in the case that we are interested, this, I mean, in other words, H Hamiltonian in the Heisenberg picture will be U dagger Hamiltonian, the Schrodinger picture, U, right? But if U is just this simplest, the simple thing that we had, right? U is e to the minus I h t minus t naught h bar. Okay, this is just hs, right? They commute, so you get. But in general, okay, plus possibly, as we said, dA h dt I h bar. Okay, the explicit time dependence. But this is the equation that one gets, no? And this,
minus n.
You see, it's minus. Okay, so then we can maybe commute this thing. So we get the quantum mechanical version of this. Okay. As usual, the Poisson bracket, right, is replaced by, if you take this on the other side, 1 over I h bar commutator, right? So this is very, I mean, the structure is very similar to the classical thing. So this is Heisenberg's picture. And actually there is a third picture that we will see, we study in quantum field theory, which is the interaction picture, which is the case where you split your Hamiltonian in an easy part that you can solve and the interaction part, right, which you don't know how to solve. I mean, very few cases one can diagonalize the Hamiltonian and sort of use the free part or the interaction part in an appropriate way that is useful for doing perturbation theory. This is called the interaction picture. This is, I mean, we will not study. You will see that, of course, in the quantum field theory, QED, and so on, right? So this is the story with the pictures. And, right. So, of course, the two pictures must, in the end, give the same physical results, otherwise it would be meaningless, right? Okay, so this is what I wanted to say about the general story, about the general formalism. And so we studied already one example of quantum mechanical system that is the two-level system. It's the simplest quantum mechanical example you can imagine, because everything is two-dimensional, 2 by 2 matrices and so on, so there is nothing simpler than that. We will come back on that, for I think I asked you some calculation to do, right? Okay, we'll discuss that. But so the other system that we are going to review, of course, that also is something that is well known to all of you, I guess, is the harmonic oscillator. Okay, so we will study that because that enters, as we will see in the quantum field theory. Harmonic oscillator enters everywhere, physics. So let me just remind what it is. Now we are dealing really with not vector spaces, but Hilbert spaces, infinite dimensional spaces. Because we have the Hamiltonian, the classical Hamiltonian is this. This is the potential is like the parabola potential. Right? This is V of x. And so this is the problem. So this is at the classical level. This describes the oscillation of a particle, right, in this potential, and is a typical, if you solve the equation of motion from this, you get the typical oscillatory, say, the typically oscillatory solution, right? X dot is, double dot is minus omega square x square, right? Then you solve this. And it's clear what is the, so there is this oscillatory behavior. There are two integration constants because it's the second order differential equation. You have two initial conditions to specify, right? And in particular, this amplitude of the oscillation is related to the energy of the total energy of the harmonic oscillator, right? The total energy, E, is proportional to a squared, right? If you plug this here, okay, is proportional to a squared. And clearly this A can vary from 0 to infinity, right? So there is a continuum of energies, right? The energy is continuous. So this is what you have at the classical level, right? Zero energy means that the particle is sitting here, is not oscillating. Then as you increase the energy, the oscillation becomes larger and larger, right, as you go up. So this is the classical story. Now the quantum story is, first of all, you have the same, the Hamiltonian is this one, but now this will be operator, right? We have this commutation relation, x p is I h bar, right? In particular, p can be taken to be minus I h d dx, no? So So then the Hamiltonian involves a differential operator, the square of this, right? So to find the possible values of the energy, you have to diagonalize. You have to find the eigenvalues. Right? H psi, say E of x, is E psi E of x, right? You have to solve this problem. Well, now this is a differential equation, second order because of this, right? So this is minus h squared over 2m d squared dx squared plus the potential applied to psi. This is the thing that one has to solve now. Not matrices, but differential operators. Okay, this can be done, of course. You can solve this, impose the right boundary conditions, right, for the wave function at infinity, and find the wave function, the form of the wave function, what the wave function is, and the energy levels, right, and one finds that actually the energy levels, let me just anticipate, we will rewrite this in another way, are given by this formula, right, where n is any positive integer, and the corresponding eigenstates are Hermite polynomials, right? The psi-n's are Hermite polynomials times some Gaussian x squared times some number here, okay? And this is the more difficult way of going into to solve the problem. Of course, these are square integrables, right? And because of the Gaussian, which suppresses the, and one can normalize. One normalizes this, right? Psi n of x star psi m of x. Dx is delta nm, right? With the appropriate normalization, here one can always adjust things like that. These are orthogonal, and when n equal to m, they integrate to 1. Okay? This is what you get if you go through this procedure. So what one see here is first, what is the difference with respect to the classical case, where the energy is not continuous, like in the classical case, but it's discrete, because it's labeled by this integer here. And also, whereas the lowest energy here is 0, the ground state is just a particle sitting at the bottom of the parabola, as you would expect, right? The ground state energy, the lowest energy state is 0, is h bar omega divided by 2, right? So this is the feature of the quantum version. The ground state is not 0 energy, but it is given by some non-zero energy, which depends on h bar and the frequency of the oscillator, right? These are the features of the quantum case. So the easiest way to solve this problem, to find this spectrum, okay, and also it allows also to find the explicit form of the wave functions, okay, without going through the solution of differential equation, is the algebraic way, right? So one rewrites this operator, this quantum operator, in terms of other operators. So first of all, it is convenient to go from xp to x, let me call x hat, p hat, okay, which are dimensionless, by rescaling. We can, if we have, what we have? We have h bar in the game, m and omega, right? These three-dimensional constants. No, with them we can construct a length and a momentum, right? By combining them. For example, h bar over m omega. This is what? This is a length square, right? No, because what is h bar? Is an action, so it's a mass, a length square over a time, right? Because it's energy times time, no? So one time goes. And so this m cancels with that. The 1 over t cancels, omega is 1 over t, of course, cancel with that. And what remains is a square, right? This is what it is. So square root of h bar m omega is a length, right? And on the other hand, momentum can be constructed by taking h bar m omega is a momentum, right? Because you get m times x over t. No? Right? So, okay. So then we can, so the dimensionless quantities are x hat is just x divided by this one, right? And p hat is p divided by this thing, right? Okay. This is because we have h bar, right? We can do that. Okay, this is just a rescaling of the variables. And then the next step is to introduce a combination of x hat and p hat to complex Hermitian conjugate operators. So A is x hat plus I p hat over square root of 2. And the x and p are Hermitian, self-adjoint. And so A dagger is x hat minus I p hat over square root of 2. No. And then, due to this commutation relation, we can compute the commutator A dagger, and what one finds is that this is just equal to 1. Okay, just change of variables, nothing more than that. Okay, so these are the variables that we will use. And then, of course, this is the Hamiltonian, as we said, is p squared over 2m plus 1/2 m omega square x squared. And one can, so if you invert this relation, right, you can derive p as a, so x will be what? X hat will be a plus a dagger over square root of 2, right? And p hat will be a minus a dagger over I square root of 2, I think. So then you can rewrite this in terms of the dimensionless variables, right? Substitute x hat, and so in terms of dimensional variable, this will become h bar omega, and then p hat square over 2 plus x hat square over 2, right? This has dimension of an energy, and this is dimensionless. No? This is what it will be. And then substitute this here, and you find what is h in terms of a and a dagger, right? But now we have to take into account that a dagger don't commute, right? The commutator of a dagger is equal to 1. So one has to pay attention to the ordering. And the standard way of writing this is this ordering, a dagger a, so first a dagger and then a, and then you find that it is something left over, which is this 1/2 here. So this is the Hamiltonian. the quantum Hamiltonian, written in terms of this A dagger. These are these variables here. Okay. It is Hermitian, of course, because the Hermitian of this Hermitian conjugate is equal to itself. There is this shift here, which is, of course, related to that. The only thing we have to figure out is what are the eigenvalues of this Hamiltonian. No? Okay. So let me rewrite them here. H is H bar omega A dagger A plus half. Now this is, as an operator, it is an Hermitian operator, which is positive, right? Because it involves, okay, this is a positive constant. The Hermitian operator times its Hermitian conjugate is a positive operator, right? Meaning it has positive eigenvalues, right? In particular, the interesting part is this, clearly, because the rest are just constants. This is what we need to know, what are the eigenvalues of, right? So this is also called the number operator, n, A dagger A. So if we find the eigenvalues of this, we are done, clear. So let's, now you know how the story goes, right? But okay, let me just review that. Suppose you take a basis of eigenstates of this n. So let me call them mu. Mu is the eigenvalue of this operator. So n mu is mu. Okay? And we know that mu is greater or equal than 0, right? Because n is positive. Okay? Now, if suppose that mu is greater than 0, then A applied to mu is different from 0, right? Why is that? Now you use an argument which is used various times in this game, is that we are working in Hilbert space, which is where there is a positive definite Hermitian scalar product defined on it. So the only way a vector can have 0 norm is if it is equal to 0, right? So what is A mu? So I claim that this, if mu is not 0, A mu, this new vector, is different from 0. Why? How do you prove that? Well, you take the norm of this, right? What is the norm of this? Well, it's this times the Hermitian conjugate, right? So this is mu A dagger A mu, right? But this is nothing but mu times mu, right? Okay? So if we started from some vector with some norm, this norm here, this is also, the norm of this is mu, right? Suppose you normalize such a way that mu is equal to 1, okay? Then the norm of this is mu, but mu is not 0, so this means that this vector here cannot be 0, right? So this is one thing that we learn. The other thing that is useful to know is what are the commutators of n with A and n with A dagger. Now, okay, this is A dagger A. I mean, to compute the commutator is very easy. You use just this, right? And what do you find? You find that this is minus A and this is plus A dagger, right? No? Because this is A dagger, A minus A dagger, right? So this is what you have to move this here. So this is a dagger A is a dagger. So let's write a dagger minus a dagger A is equal to 1. So this is A dagger A is a dagger minus 1 minus a dagger, right? And this is minus A, right? And the same for this, you get a plus. Okay, so then what do we learn? We learn that if we apply A on mu, this is an eigenstate of n, capital N, with eigenvalue mu minus 1. Right? Because n A on mu is A n mu minus A mu, right? But this is mu, right? So this is mu minus 1 A mu, right? So this is eigenstate of n with eigenvalue minus 1, decreases by 1. And as you know, if you apply instead a dagger, you get that this is up to normalization. This means that there is a possible normalization here, okay? We assume that these vectors are normalized to 1 for simplicity, then it may be there is some constant here, right? So, and this is, of course, belongs to mu plus 1, right? In the same type of calculation. So for this reason, so A is called annihilation operator, or also sometimes rising operator, and a dagger is creation, right? Oh, no, sorry, lowering. This is lowering, right? And this is raising. But in this context, these are called annihilation A and creation A dagger. Okay. So how can we sort of fix at the moment this mu, the possible value of mu are we don't know much about that, right? But the point is that mu must be a non-negative integer. Okay, this is the statement that I want to make. Actually, so mu has to be 0, 1. Why is that?
Shouldn't that be whole numbers?
Sorry?
As you said that mu is element of natural numbers, but they start from 1. Mu can also be 0.
Yeah. Mu can be 0, yes.
So it belongs to the whole numbers, not natural.
Non-negative.
N means non-negative integers.
Yeah.
Okay.
You mean and
Okay.
yeah, this is non-negative. This by n means I mean this, and sometimes just to be sure about the notation, if you find this notation, then this is 1, 2, and so on. Okay. This is used also R. Say R with the plus means the positive reals, and so on. Okay. But if there is if I don't have this, this means that there is 0 is included. Okay. Why is that? Well, this comes from two facts. One is that this mu has to be greater or equal than 0, and the fact that A applied to mu decreases the value of mu by 1 each time. If And of course, what we know also that if mu is equal to 0, okay, if mu is equal to 0, A0 is what? Is 0, right? By this type of argument here, right? Because the norm is 0, so it must be 0. Okay, so what is the argument for picking the integers and not arbitrary real, positive real numbers? The point is that, you know, if this were an arbitrary real, positive real number, by applying enough powers of A, right, you go down, no? You start from mu minus 1, and so on, right? But this process never ends, right? Because the resulting eigenvalue cannot be 0, never be 0, right? If you start with a real number, which is not integer, and you decrease by integers, you will never get 0, right? Yeah, this process will go down to minus infinity, right? You agree?
Yeah.
So there are these two facts, that the fact that the spectrum must be non-negative and the fact that A decreases by step of 1 each time, then you must assume that mu is an integer, because then after some steps you get 0. And if you get 0, then nothing, you don't do anything anymore, right? Because A on 0 is 0, so the story ends here. Okay? So this is a result of these two facts here. This and the positivity. But then we cannot say about anything about the top part of the spectrum. That can go up to plus infinity, right? Okay. And so you go up and down. You go down by using A until you reach 0, in which case the procedure stops here, because there is nothing more you can do after that. But with A dagger you can go up to infinity, right? By applying enough powers of A dagger you can increase the eigenvalues arbitrarily. Okay? So this is the conclusion then. So we establish the spectrum. So you see, this is this type of argument, the fact that there is some shortening in the spectrum, in this case it's just on one side, not on all sides, due to these commutation relations here, is a fact that you will see also when you study representation of issue 2. Also there you have raising and lowering operators, J plus and J minus, right? In that case though, you have on both sides the spectrum terminates, right? Both of the upper side and the lower side. No? This the familiar fact that the representation of issue 2 are finite dimensional. Right? In this case, this is different algebra. The algebra is called Heisenberg algebra. It's just this. This is the algebra. You may regard it as a Lie algebra, particular case of Lie algebra. Remember SU2, just to recall, right? You have J plus, J minus, which have the analog of this is 2J3, and then you have J3, J plus minus is plus minus J plus minus, right? This is SU2. So it's very different from that, right? Only this part looks like that, but in this case there is just one on the right hand side, not this J3 operator. So it's a very different from SU2. This is, in fact, this is called semi-simple algebra. This is not, okay? But you will see that in the course. So this is, so we have established the fact that one can derive, as I said, by solving the difficult ways to solve differential equations with boundary conditions, and that give the same result. So, conclusion is that the energy levels are this, right? And as I said, there is the distinctive feature of the 0-point energy. This is the ground state energy. So there are two features which are typical of the quantum situation. One is the discrete spectrum. The other is the 0-point energy. So in the classical case, the 0-point energy is 0, and the spectrum is continuous. The discreteness of the spectrum is not just a feature of this very symmetric potential, right? If I had a potential like this, for example, I mean something, you write a random thing which goes on both sides to infinity, you wouldn't be able to find the spectrum, but one thing that you would know is that the spectrum, there will be some discrete spectrum. This is feature of potentials that's called confining potential, okay? For which, what is the feature of this potential is that if you have some energy here, right, the particle is confined in this region, right? It cannot go in this region. This is classically avoided region, right? Quantum mechanically, the situation is different because all you know is there's some wave function. The wave function is, you know, is concentrated around the origin, but it can go also at infinity very slowly, very rapidly actually, right? But it can go. So there is a probability of finding the particle also here, right? Quantum mechanical. Right. So these are all things that I guess you know very well. And we will discuss, so these are states, so the eigenstates of the Hamiltonian are labeled by this integer here, n, right? These are the eigenstates of the Hamiltonian. It's a basis where the Hamiltonian is diagonal. And maybe we will study something that I don't know if all of you have ever studied, is different kind of states which are called coherent states, which have a nice interpretation. So this will be our sort of non-standard discussion about the harmonic oscillator. Okay, coherent states, we will see soon what they are, but at the moment we are dealing with these states, and they are supposed to be normalized, orthonormalized, right? And to do that, of course, how do we get this n? Well, we know if we start from the ground state, 0, we can get level n by applying a daggers, right? From that file. So a dagger to the power n on the ground state gives something proportional to n. We have to fix the normalization though, because this need not be normalized to 1. So n will be for sure this times some constant, and the constant you have to fix it by computing what? The norm of this state, right? Compute the norm, you find that it is not 1, so you have to divide this by the square root of that, right? And what happens is that this is square root of n factorial. Why is that? Because if you compute the norm of this state, you have a dagger to the power n. and this is a to the power n, right? This is the norm, right? What is the procedure to do that? Well, you have to move the annihilation. If you move an a here, you get 0, right? And so you have to move all these a's on this side, and then, but something remains, right? And what remains is an n factorial, right? Because you have, the first time you get n, the second time you get n minus 1, and n minus 2, and so on. This makes an n factorial if you collect all the terms. And so you have to divide this by the square root of n factorial in order for this to be normalized to 1, right? Of course, they are orthogonal to each other, n and n, because if you take a dagger to the n and a dagger to the m, right? If n is different from m, they are orthogonal to each other. Again, you compute the scalar product of this with that, right? You have 0, a to the m, a dagger to the n. And if this is different from that, you find that this is actually 0. Okay? Nothing remains, so they are orthogonal. So this is the basis of an orthonormal basis for our problem, right? This. And of course, some extra useful identities are A acting on n and a dagger acting on n. This you expect to be n minus 1, right? This you expect to be n plus 1, right? But again, you have to compute norms, right? And I guess this is square root of n, and this is square root of n plus 1, probably. You have to check it. Okay. So this is, so now we know everything about the Howard Hilbert space. This is the basis. Now it's a truly an Hilbert space, right? It's not a vector space, finite dimensional vector space. And so then when you form linear combinations of these objects, right, an arbitrary state will be some Cn n, right? But then this Cn's, the fact that, of course, psi must be equal to 1, this says that sum from 0 to infinity, Cn mod square is equal to 1, right? So this Cn has to decrease with n rapidly enough to make sure that this gives a finite, gives a convergence, of course. Yeah. This is the, yeah. In fact, we will study precisely the coherent states are precisely of this form here, where this is an infinite sum, because, okay, you can always restrict to a finite sum, right? You choose a finite combination of n's, that is also a state, there's no problem with that. But the coherent states, we will see, involve this sum. Really, all the Cn's are different from 0 to infinity. Okay? That will be the discussion we'll have maybe next time. Okay, and yeah, what about yeah, what next? Yeah, this, okay, is nice, but it sounds somewhat abstract because, okay, I mean, you may say, well, I would like to know, for example, given the wave function, say the ground state is just this state, right? What is the corresponding wave function? Meaning, psi is 0, let me call it psi 0 of x, what is it? It is just, no, we said the other time, is formally this thing here, right? You have to project on the x basis, no? So what is this function? It's a Gaussian, right, as you know. And how do you get it? Eh?
the terms of these from the new grid?
Differential.
Sorry? No.
From the differential. Schrodinger.
From?
Schrodinger.
What Schrodinger?
For the harmonic oscillator solving the equation.
So in practice? In practice? No, I mean, you said something, so...
I said something.
Yeah, but try to explain what you mean. Yeah.
You mean how do I get the wave function?
Oh, you get, yeah.
Yes, only solving Schrodinger equation for the case of the lowest energy.
You mean the equation, differential equation?
Yeah?
Yeah, that, of course, but what I'm saying is that there is an easy way.
Ah, listen.
Yeah, the easy way. You know an easy way to do that.
We can see
Minimum
that
uncertainty.
A0,
Minimum uncertainty.
we say A0 equal to
Sorry?
A0 equal to 0.
Yeah, that is the key. The ground state is characterized by this condition, right?
Yeah.
Now, the advantage of this, is that this is a first order differential operator, right? X, because this A is X hat minus I P hat over square root of 2. Right? So this is 1 over square root of 2, this is X hat, and this is, P is, we said, minus I dx, right? No, this is plus. So this is plus d dx hat, right? No? X hat, p hat is I, right? There is no h bar. H bar goes away because we rescaled, right? So that this means that p hat is minus I d dx hat. So the only thing, there is no h bar, right? So you have this. So psi 0 satisfies the Schrodinger equation, but Schrodinger equation is second order differential equation. It's more complicated, right? You can do that, of course. But this is a first order. So if we now we have this condition means that, well, x hat plus d dx hat on psi 0 of x hat is equal to 0, right? But that we can easily solve, right? Because what is the solution of this? This is precisely the Gaussian. Right? This is psi 0 of x hat is some constant e to the minus x hat square over 2. No? And now you substitute, if you want to go with the physical x, you substitute x hat is this h bar m omega combination times x divided by that, you find the Gaussian in x space, not x hat space. But this is ground state, which is a Gaussian, as you can see here. Right, no? Because when you apply ddx, you differentiate this, you get a minus 2 cancels this 2 and x, and that x cancels this x, right? Right? So the ground state, we obtain it very easily instead of solving the Schrodinger equation, which is the correct but difficult way. We just solve this very trivial differential equation, right? First order. Okay, so far from the ground state. What about the excited states? Can you get the differential, the wave science for the excited state?
Yes, acting with a
Yeah. Acting with the creation operator, which are again differential operators, because if this is A dagger is just 1 over square root of 2 x hat minus d dx hat. Notice that, maybe just a remark, why you say it's a bit strange, right? Why there is a plus here and a minus here? Because there is no I here, right? Yeah, the point is that should recall that the derivative ddx is anti-Hermitian. No? The I precisely makes it Hermitian. So when you take the Hermitian conjugate of ddx, you get a minus, right? Okay, because it acts on the space of functions. You have to do partial integration. Okay. And so you apply, so the first excited state will be x hat minus ddx hat on this, right? On the ground state wave function. It will be a first order polynomial times always the Gaussian. The Gaussian is always there, right? And this is what makes the wave functions square integrable, right? And if you put the correct normalization, you are bound to get the correct normalized wave function. So in this way you get the mid polynomials. Because if you go down, keep going with n, a dagger to the, so a dagger square is a second order polynomial, second degree polynomial, and so on, right? So the ground state is just very simple, is the Gaussian here. So it's very much concentrated, this is the potential, right, around the origin, but it's a trivial wave function, there is some spread, right, and this is the reason for the 0 point energy there, right. And then the first excited state would be a first order, so you see this has, this wave function is never 0, right, it goes to 0 to infinity, but it never crosses the x-axis, right? But now, when you go to excited states, there is a general fact of quantum mechanics that the number of nodes of the wave function, which is the number of crossing of the x-axis, is related to the energy, right? So the more excited you have the state, the more crossings you get. This is a general fact in quantum mechanics. So the first excited state will be, it's a linear, right? Because x ddx is something proportional, no? If you psi 0, so if you want psi 1, this is proportional. Both give an x, right? There is an x here. This, when it acts on the Gaussian, get another x, right? So it's something x hat e to the minus x hat square over 2, right? And so this is the Gaussian, right? The ground state. This x is a linear function, so there will be something like this, right? Probably. Something like this. No? Must go to 0 in any case. This is psi 0. It crosses 0 at the origin. This is psi 1. Right? And of course, what is more meaningful is the modulo square of psi, because that gives the probability density, right? Probability densities, say Pn of x is given by psi n modulo square, right? This gives the probability of finding, when you integrate this over the whole axis, you get 1, so, of course. But if you integrate in some region, it gives the probability of finding the particle in that region, right? Which is less than 1. And so this will give, if you square this, okay, you find something like this, right? I guess. Right? You must be positive always, right? Okay, this is the way it is. And then, as you move with n, you get all the mid polynomials, even and odd, okay, depending on n, right? So this is the So this is the easy way to go about solving the harmonic oscillator. And you get all the information that you want, that you get from solving the Schrodinger equation. There is no, not just the spectrum, I repeat, but also the form of the wave functions. Okay? Fine. So, yeah, any question about this? Notice that this is a single harmonic oscillator. You can always have a collection of harmonic oscillators which are decoupled, like what I mean is the following. This with what we will have in actual application to quantum field theory, right? It's not just a single harmonic oscillator, but a collection of harmonic oscillators. So if you have a polynomial, a Hamiltonian, which is, say, p squared over 2m plus 1/2 m omega squared x squared. Say, suppose you are in 3 dimensions, okay? So there are 3 decoupled harmonic oscillators, right? Because x1, x2, x3, they are not interacting with each other, right? Moreover, the simplest case is where they all have the same frequency. You may have also cases where the frequencies of the 3 directions are different, right? But this is just the sum of 3 independent Hamiltonian, right? H1 plus H2 plus H3. But these 3 Hamiltonian are identical, right? They are the same Hamiltonian, right? So the spectrum, the wave functions are just a collect. I mean, for instance, the spectrum, what it will be? It will be E H bar omega n1 plus half, right? Plus n2 plus half plus n3 plus half, right? No? So you see, if you add harmonic oscillators, the ground state wave function adds, right? You get enough factor from each harmonic oscillator, right? So this will, as you will see, is a problem, okay? Is a little problem. If you have an infinite number of harmonic oscillators, then how to make sense of these infinite sums, right? You have an infinite sums of 0-point energies, right? So that you have to take care of course. This is added in the application of where the harmonic oscillators enter in quantum field theory. This is always the case. There are infinite set of harmonic oscillators, okay? And there is, you have to make, handle this problem of what is how to make sense of this infinite, sum of halves. No? But for the final number, okay, this is what it is. And so you have 3 integers, you see, n1, n2, n3. Right? The energy levels are characterized by these 3 integers. Specify each of them gives. So there is a degeneracy for the energy, because you can get many ways you get the same energy level by arranging 3 integers, right? The point is that you have to, the sum over n i's is equal to n. The number of ways you can arrange integers in such a way that their sum is equal to some capital integer n is the degeneracy of the level n state, right? Whereas in the single harmonic oscillator there is no degeneracy. So there is a degeneracy. For example, trivial case. Suppose you have capital N equal to 1. What is the degeneracy?
1.
Not 1.
1,
3.
0, yeah.
Because you can have 1, 0, 0, 0, 1, 0, 0, 0, 1. Right? There are 3 possible ways to get 1 summing 3. No? and so on, right? If you have a capital N equal to 2, you can have 1, 1, 0, 0, 1, 1, 1, 0, 1, but then you can have 0, 0, 2, 2, 0, 0. No, you have 6 probably. And so, of course, the degeneracy keeps growing with n, right? Very, I mean, it grows very rapidly. So this is not a problem. This can be, I mean, once you solve the single harmonic oscillator, you can solve the system of harmonic oscillators, and then you can also have the case where there are different frequencies along the 3 directions, in which case you have to put omega 1 here, omega 2, omega 3, and okay. So this is not a conceptual issue. So this more or less is all we want to know about that. Okay, once more, maybe we can see, I think we have a lecture tomorrow to compensate for the missing one of yesterday in the afternoon. I don't know if secretary told you. At 2 tomorrow. Okay, maybe we discuss some. Yeah, now what I wanted to ask you is to do this little calculation with this. So you have these states n. One may ask, what is the, so, and then we have x, operator x and p, right? It is, okay, of some interest to compute the variance delta x and delta p in the state n generic n, and see how it behaves with n. The n dependence. Delta x is, you know, no? Delta x is, say, you have to compute x square minus x square, and similarly for p, right? And x, n, and p and n, x square, right? Yeah, to do this calculation, what you do? You expand x and p in a dagger, right? And you use the, okay. And then finally, once you have that, you compute delta x, delta p, how it behaves as a function of n. Okay? And you will see that it grows, delta x with delta p, this uncertainty grows with n. Okay? The ground state for n equal to 0, what you would expect? This is a Gaussian. I would expect the minimal, the Heisenberg bound to be saturated. For n equal to 0, I would expect delta x, delta p is h bar omega. Sorry, no, h bar over 2, no? This is what I would expect for n equal to 0, but for generic n, for higher n's, this actually should grow, not remain the minimal one. Okay? They should go linearly with n, actually. And, okay. So we will see that there are, the nice thing about, so this says, goes like n, say, proportional to n. This is what you should get. This says that these n's, you know, when these states are very far from classical states, right? Because for states which are close to semi-classical or classical situation, you would expect the minimal uncertainty, right? There is always an uncertainty, that is no way we can avoid this, right? H bar over 2. But for states which are close to the classical picture, it should be minimal one, right? Instead, if they go like n, the bigger n, the bigger is this the violation of the bound, and so they are not physically, they are not close to classical state. So that is why we will study states which are instead, they always saturate this bound. These are the coherent states. Okay, they are also sometimes called semi-classical states for this reason, because they always saturate this bound. Okay. All right. And okay, now, yeah. So you had some work, maybe so you can give it to me, and then we discuss it tomorrow, or next time in any case. I thought, I don't remember now, some of you last time did not put his name. You, okay. Okay.
This is the recording?